Looking to the future with Willow, we continue our journey towards building large-scale and useful error-corrected quantum computers that will push the boundaries of science and the exploration of nature.
What if a quantum computer could peer beyond the universe itself, before time as we know it even existed? Google's cutting-edge quantum chip, Willow, might just be able to do that with its latest breakthrough discovery. Scientists are exploring whether this breakthrough could be hinting at a structure that predates the universe, a discovery that could shake the very foundations of physics.
We survived.
Somewhere in their fifth dimension, they saved us.
Could this mean the cosmos had a past before the Big Bang? Or are we looking at something even stranger? Let's dive into this mind-boggling discovery that shocked the entire world. Before we can even begin to understand how Willow might uncover a structure older than the universe, we need to talk about what makes it so special. Quantum computers are not just super-fast versions of regular computers, they work in a completely different way. And Willow is pushing the boundaries of what was once thought possible. Google's Willow is one of the most advanced quantum chips ever created. Unlike classical computers that process information in binary, zeros and ones, Willow operates using qubits, quantum bits that can exist in multiple states at once due to a phenomenon called superposition. This allows quantum computers to perform mind-boggling calculations exponentially faster than even the best supercomputers. But speed isn't the only advantage. Another key feature of quantum computing is entanglement, where qubits become interlinked, meaning that a change in one instantaneously affects another, no matter the distance between them. This interconnectedness gives quantum computers an almost eerie ability to solve problems that classical machines simply can't. What makes Willow unique is its ability to handle more qubits with higher stability than its predecessors. One of the biggest challenges in quantum computing is quantum decoherence, where qubits lose their state due to interference from the environment. Google has made significant strides in error correction and qubit stabilization, making Willow one of the most reliable quantum chips ever built. This means Willow isn't just some experimental toy. It has the power to simulate complex quantum systems, potentially unlocking secrets that have remained hidden for billions of years. Traditional computers struggle with simulating the behavior of particles at the quantum level, but Willow could bridge that gap, giving scientists a new lens to explore physics beyond our current understanding. So how does this tie into a structure older than the universe? Quantum physics suggests that space-time itself might be woven from quantum interactions at the smallest scales. If there are anomalies, traces of something that existed before the Big Bang, Willow might be our best shot at detecting them. It could simulate early universe conditions, test radical theories, and reveal whether our reality is just one layer of something even deeper. But what exactly is this supposed structure that might defy our understanding of time? Let's break it down. Did scientists just find something that shouldn't exist? If Willow is as powerful as it seems, what exactly is it trying to find? There's a growing buzz in the scientific community about a possible structure, something so old, so fundamental, that it might have existed before the universe itself. But how is that even possible? In physics, the Big Bang is considered the starting point of everything: space, time, and all matter. But what if that's not entirely true? Some astronomers and physicists have observed cosmic anomalies that don't quite fit within our understanding of time's beginning. These could be quantum remnants from a previous universe, unexplained energy signatures, or structures that appear too large and too ancient to have formed within the 13.8 billion year lifespan of our cosmos. One such anomaly is the so-called cold spot in the cosmic microwave background, CMB. The CMB is the faint glow left over from the early universe, but this particular region is strangely empty, almost as if something massive had disrupted it. Some scientists suggest this could be evidence of a collision with another universe in a past cosmic cycle. Others argue it might be a quantum imprint from before the Big Bang. There are also strange voids and giant cosmic structures that seem to defy conventional physics. Structures like the Hercules Corona Borealis Great Wall, a mind-bogglingly massive cluster of galaxies, shouldn't exist according to the timeline of cosmic evolution. It's simply too big to have formed in the time available since the Big Bang. Could it be something even older? This is where Willow comes in. Traditional computers struggle to model these vast and complex anomalies, but quantum computing could simulate how such structures might have formed, or whether they existed before the universe as we know it. If Willow can process quantum fluctuations in extreme cosmic conditions beyond what's currently possible, it might provide the first real evidence that the universe had a history before the Big Bang. And if that turns out to be true, it changes everything. It could mean that time didn't have a beginning, that our universe is just one iteration in an endless cycle, or that something much deeper, something more fundamental, underlies all of reality. But how do you even begin to simulate the birth of the universe, or something that came before it? That's where things get really interesting. Are we about to recreate the beginning of everything? If there really is something older than the universe, how do we prove it? The answer might lie in simulating the birth of the universe itself, a task so complex that only quantum computers like Willow might be able to handle it. The first fraction of a second after the Big Bang, known as the Planck epoch, is one of the biggest mysteries in physics. It's the point where everything, matter, energy, space, even time, was so compressed that the laws of physics as we know them simply break down. Gravity and quantum mechanics should merge in this extreme state, but no classical computer can model what actually happened. Willow, however, might be able to simulate these conditions and reveal whether something predated the universe. Quantum computers excel at simulating the behavior of particles and forces at subatomic scales, where classical physics stops making sense. This means Willow could reconstruct scenarios of what happened at the Planck scale, testing theories like quantum loop gravity, which suggests that space-time itself is quantized. If true, this could mean the Big Bang wasn't the beginning, but a bounce from an earlier universe. Another possibility is vacuum fluctuations, the idea that the universe emerged from a temporary quantum disturbance in a vacuum. The laws of quantum mechanics suggest that even empty space isn't truly empty, it's constantly bubbling with fluctuations of energy. If Willow can simulate these fluctuations with high enough precision, it could test whether the universe spontaneously emerged from a quantum state rather than from absolute nothingness. Then there's the holographic principle, which proposes that our entire three-dimensional universe is just a projection of information encoded on a lower dimensional surface. This is a radical idea, but it could explain many mysteries in physics, including the strange nature of black holes. Willow has the potential to simulate lower dimensional quantum systems and compare them to our universe, providing evidence for or against the idea that we're living in a vast quantum projection. Each of these simulations could provide answers to questions we never thought we could even ask. Did time exist before the Big Bang? Was our universe born from a quantum fluctuation? Could we actually be part of something much larger? And if Willow does find something, some anomaly, some unexplained pattern buried deep in the quantum fabric of space, it could be the first real sign that the universe wasn't the beginning. But if our universe wasn't the first, what came before? What if the universe has been reborn over and over again? If the Big Bang wasn't truly the beginning, then what came before? One of the most fascinating theories attempting to answer this is loop quantum gravity, LQG, and the Big Bounce hypothesis, an idea that suggests our universe is just one in an infinite cycle of expansion and collapse. And quantum computing, particularly Willow, might be able to put it to the test. For decades, physicists have struggled to reconcile general relativity, which describes gravity on a cosmic scale, with quantum mechanics, which governs the tiny world of subatomic particles. The equations of general relativity break down when you rewind the universe all the way back to the Big Bang, leading to an impossible singularity, a point where density and temperature become infinite. That doesn't make much sense, and it suggests that something is missing from our understanding of the universe's birth. This is where loop quantum gravity comes in. Instead of seeing space-time as a smooth, continuous fabric, LQG suggests that space itself is made up of tiny, discrete loops, like a woven network. These loops prevent gravity from collapsing into an infinite singularity, meaning the universe never actually reaches a true beginning. Instead, when it reaches maximum density, it bounces back, expanding again in a new cycle. This is the Big Bounce hypothesis, a never-ending cycle of universes being born, expanding, collapsing, and then rebounding into a new one. In this view, the Big Bang wasn't a singular creation event, it was just the latest restart of an ongoing cosmic process. If true, This could explain why scientists are detecting structures in space that seem too old to fit within our universe's timeline. They might be remnants from a previous cycle. But how does Willow fit into this? Unlike classical computers, which struggle to model gravity and quantum effects together, a quantum computer can process quantum-scale fluctuations in space-time, testing whether LQG's predictions hold up. Willow could simulate how space behaves at the smallest possible scales, potentially revealing whether the universe's expansion is truly the beginning or just another phase in an infinite cycle. If the Big Bounce is real, it would completely change our understanding of reality. It would mean time didn't start at the Big Bang. It would mean our universe isn't unique. It's part of an endless chain of cosmic rebirths. And if Willow finds real evidence for this, it might just prove that our universe has been dying and being reborn long before we ever existed, and will continue long after we're gone. But what if our reality itself isn't what we think it is? What if the universe is just a projection? If the Big Bang wasn't the true beginning, and the universe has been cycling through endless rebirths, then we have to ask, what exactly is our reality? Some physicists believe we might be looking at everything the wrong way. Instead of existing in a three-dimensional universe, we could be living inside a massive hologram. And quantum computing, especially Willow, could be the key to proving it. The holographic universe hypothesis suggests that our entire reality, everything we see, feel, and experience, might actually be a projection of information encoded on a distant lower dimensional surface. This isn't just science fiction, it's a serious theory backed by physics, originally inspired by the way black holes store information. Here's the idea: when something falls into a black hole, its information isn't lost. It gets encoded on the black hole's surface, much like how data is stored on a 2D hard drive but appears as a 3D image on your screen. Some scientists believe the same principle might apply to the entire universe. The 3D reality we experience could be an illusion, with all of its underlying information stored on a cosmic boundary far beyond what we can see. This theory could explain a lot of weird things in physics, especially in quantum mechanics. For example, particles can become entangled across vast distances instantly, almost as if they aren't really separated in the way we think. If the universe is truly a hologram, these kinds of strange quantum connections make more sense. They wouldn't be distant at all, because the true reality exists in a different way than we perceive it. So where does Willow come in? Quantum computers like Willow are uniquely suited to test this theory. Unlike classical computers, which process data in a rigid step-by-step manner, quantum computers naturally operate in a way that aligns with holographic principles, storing and manipulating vast amounts of quantum information in ways that don't follow normal three-dimensional logic. By simulating lower-dimensional quantum systems and comparing them to real-world physics, Willow might help determine whether our reality is truly emergent from a deeper hidden layer of information. If this turns out to be the case, then everything we know about space, time, and even consciousness could be part of a much larger cosmic structure, one we've only just begun to understand. But if our universe is a projection, what does that mean for everything beyond it? What if our universe is just one of many? If the universe is a hologram, then what about everything beyond it? Could there be other universes, each with their own laws of physics existing parallel to ours? One of the most mind-bending possibilities in modern physics is the multiverse hypothesis, and quantum computing might be the only tool capable of proving it. At the heart of this idea is eternal inflation, a theory suggesting that the rapid expansion of space didn't just happen once during the Big Bang, but has been happening forever in different regions of the cosmos. While our universe expanded and slowed down, inflation could still be happening elsewhere, constantly spawning new universes like bubbles in an endless cosmic foam. Each of these universes could have entirely different physical laws. Some might be similar to ours, while others could have completely different fundamental forces, different types of particles, or even no time at all as we understand it. If this is true, then our universe is just one of countless others, each existing in an infinite cosmic landscape. But how do we even begin to test this? Traditional computers struggle with calculations involving infinite possibilities, but quantum computers like Willow thrive in this environment. Since quantum mechanics itself suggests multiple possibilities coexisting at once, like superposition in qubits, Willow might be able to simulate scenarios where multiple universes arise from eternal inflation. One potential piece of evidence comes from cosmic anomalies, strange patterns in the cosmic microwave background radiation that some scientists believe could be imprints from another universe colliding with ours in the distant past. If Willow can simulate these events, it could help determine whether these anomalies are just statistical noise or actual signs of another universe brushing up against our own. If the multiverse is real, it changes everything. It means our universe isn't special, just one of an infinite number of possibilities. It also raises deeper questions. Could other versions of us exist in different universes? Is there a way to communicate across these cosmic boundaries? And most importantly, if our universe is just one bubble in an infinite sea, then what else is out there waiting to be discovered? Did the universe just pop into existence out of nowhere? If the multiverse is real and cosmic inflation is still happening somewhere, then a bigger question emerges. Where did everything come from in the first place? Did the universe require a cause, or could it have simply emerged from nothing? As bizarre as it sounds, some physicists believe that quantum fluctuations might hold the answer. In classical physics, nothing means complete emptiness, no matter, no energy, no space, no time. But quantum mechanics doesn't quite work that way. Even in a perfect vacuum, tiny energy fluctuations are constantly appearing and disappearing. These quantum fluctuations mean that even the emptiest space isn't truly empty. It's teeming with brief bursts of energy, creating particles and antiparticles that pop in and out of existence. Some theories propose that the entire universe could have emerged from one of these fluctuations. If a quantum fluctuation occurred in just the right way, it might have tunneled into existence, rapidly expanding into the universe we see today. This would mean the universe didn't need a cause in the traditional sense. It could have simply happened due to the laws of quantum mechanics. But testing this idea is extremely difficult. Classical computers struggle to simulate quantum fluctuations at the scale needed to model an entire universe. This is where quantum computers like Willow could step in. Since Willow operates on the same principles of quantum mechanics, it could potentially simulate vacuum states, quantum tunneling, and even the birth of the universe itself. If Willow can accurately model quantum fluctuations in extreme conditions, it might help determine whether a vacuum fluctuation could have triggered the Big Bang, or if some deeper unknown process was at play. It could also help answer another mind-bending question. If universes can emerge from nothing, is this process still happening somewhere right now? And if universes can spontaneously appear from quantum fluctuations, does that mean our own existence was just a random accident? Or is there something even deeper governing it all? What if time itself is just an illusion? If the universe could have emerged from a quantum fluctuation, then here's an even stranger thought. What if time didn't exist before the universe because time isn't fundamental at all? It's a wild idea, but some physicists believe time may not be a basic building block of reality, but something that emerges from deeper physical processes. In our everyday experience, time feels like a constant flow, past, present, future, but when you zoom into the quantum scale, things get weird. In quantum mechanics, particles don't have definite positions or states until they are measured. They exist in superpositions, meaning they occupy multiple states at once. If this applies to the universe itself, then time, our sense of a before and after, might just be an illusion that arises from the way we perceive quantum interactions. One of the most radical ideas is that the universe exists in a timeless quantum state, where everything, past, present, and future, coexists simultaneously, but only appears to unfold due to our observation. This is supported by some interpretations of loop quantum gravity, which suggest that at the smallest scales, space and time break down into discrete quantized units rather than flowing smoothly like we experience. If true, this would explain why trying to pinpoint a beginning of time like the Big Bang becomes meaningless, because time itself might not have existed in the way we think. The universe may not have started at a single point, but rather transitioned from a timeless quantum state into the expanding cosmos we see today. How does Willow fit into this? Since quantum computers operate in ways that don't rely on classical time-dependent processing, they could be the perfect tool to model a universe where time is not fundamental. By simulating quantum states without the assumption of linear time, Willow might help test whether the passage of time is just an emergent property, one that only exists because of how we interact with the universe. If time is just a construct, it completely reshapes how we think about existence. Could there be realities where time moves differently, or universes where time doesn't exist at all? And if time isn't fundamental, what does that mean for concepts like cause and effect? It would mean that asking, what happened before the Big Bang, might be the wrong question entirely, because if time itself isn't real in the way we think, then maybe nothing actually came before.